Welcome everyone to this exciting AI Fest, and thanks to Orbit Shifters, Mahesh, Narendra, and Prashant, and others. It's a great privilege to be here talking to you all about the upcoming business disruptive technology called artificial intelligence. So I know it's a great technology to talk about, but what I'm going to talk about today is something like what is the basic nuts and bolts of AI? What does it mean? What kind of business applications is it applicable for? And what are the constituent technologies which enable us to say a system is made of AI? So in the next 45 minutes to 50 minutes, I'll try to onion peel in a very, what you can say, a 360-degree view of AI. And in doing that, I hope I will be able to resolve a very basic level of understanding for everyone out there in the conference, get a perspective of AI, which is more like a layman. I'm not so much deep into the intricate algorithms per se, but what I will try to cover is the technology landscape of AI, what kind of techniques are there overall in the AI domain. So given that, let me start with a brief perspective of what I'm going to talk about. Today, I'm actually talking about different notions of AI or artificial intelligence as we talk about. And while doing that, I will also mention that it's not like everyone has the same perception of AI. So there are different levels of AI depending upon whom you talk to and how you perceive as the level of the AI system. Then what we will do is I will go ahead and talk about what is the basic constituent technology spectrum of AI, which is making all this kind of possibilities of AI real. Then I will move on to a very basic, you can think about the brain of AI, or we call it machine learning, which is the emergent technology which is enabling the success stories of AI as we see. Then we will also look at, when I talk about machine learning as the brain of AI.
Srini sir, sorry to disturb. Someone has taken over your screen share. So can you do the screen share again?
Oh.
Guys, just be careful. Do not take over the screen share. So sorry to disturb you, sir.
Okay. Is it fine? Is it visible now?
Yes, sir.
Okay, so when I say machine learning as the brain of AI applications, you need to also understand that it's again not one size fits all. There are different varieties of these machine learning techniques as applicable in different areas. So what we will look at is the different types of ML in a very, very high level view. Then what we will look at is when I say a machine learning as a brain of AI, it's just not like it is possible to do this with a simple technology. It's about powering them by different algorithms. I'll just give a broad eye view of the different algorithms which power this AI. Then move on to a subset of AI which has become the darling of the community and which has enabled emergence of AI from the shadow, namely deep learning, which is again a subset of machine learning. Then we'll see where deep learning fits with respect to the overall spectrum of AI machine learning. And in the last, we'll just cover some of the emergent opportunities which are emerging, which are real, which are practical, and very close to home in terms of applications of AI ML all around us. So given this, let me start by a very high level view of what we mean by AI. AI, if you see, it is a broad set of technologies which enable us to imbibe intelligence into machines. So when I say intelligence into machines, there are two things which comes to the mind. what is intelligence. Second is what is a machine. So when I say machine, machine could be a software, it could be a hardware, sensor, or it could be hardware embedded with intelligent software. But when it comes to intelligence, it is about mimicking human behavior as close to perfection, as close to the level of agility of humans, as close to the level of experience as a human would, and that would define intelligence to me. It's about mimicking human behavior. That's the whole idea. So we define both sides. One is who is going to imbibe such behavior. It's a machine. We in fact in AI terms we call it an agent. So we call it an intelligent agent. So AI is also sometimes technically known as the study of intelligent agents. So agent is, again, as it's defined, it could be a simple software piece, like for example a chatbot sitting on your bank website portal, listening to queries, answering them. Or it could be a hardware robot which is having inherent intelligence and walking around. So we need to look at all the aspects of the machine intelligence when we talk about not just the aspect of software, but also about the possibilities of hardware manifestations of such things. So when I say mimicking human behavior, does it mean that we talk about all the kind of AI systems display same level of proficiency, same level of humanness, same level of performance as a human? The answer turns out that today we talk about 3 different levels of performance, and these are not something which is very, very different from what we see in the general gradation of absorption of technology. So whenever we absorb any technology, it's not like everybody is proficient at the highest level. It goes in phases. So even in AI, we talk about 3 levels of proficiency. So the first one, which is what we commonly see and we see tons of examples of, is the notion of AI that's very good at performing a very simple task. And then when we talk about performing a simple task, it's also important to understand that the notion of simple is so simple that it is one narrow, small, single task. When I say simple task or a single task, it's important to understand that the machine which we have built to mimic human performance for that single task, it may be better than even the best human in that task. So let's take the example of chess. We have a very good set of AI programs today. Like Deep Blue was like quite a decade ago, but today we have really, really fast chess playing programs based on different AI algorithms, which beat human champions, grandmasters. Same way, let's take a complex game like Go or poker. Today we have AI programs like AlphaGo, which beat Go champion in the world-class championships. Same way, we have different AI programs being at the verge of defeating several human champions in each of their vendors, each of their games. But then question comes, okay, I have built a very, very special purpose engine, which is very good at playing Go, which beat human champion. That's what we call as narrow intelligence or narrow AI or weak AI. And today we have seen several such success stories of AI. Let us say we have built a car which is very good for driving autonomously in the suburbs of California, because it knows that area very well. But now I have to throw a challenge. The challenge is, if suppose I trained the system on streets of California, I take the same car which is trained on streets of California and I take it to, let us say, streets of Mexico. Will it go and perform at the same level of autonomy and without any errors? Will it be able to perform replacing a driver? The answer turns out to be no. Same thing, a Go champion like AlphaGo, can I go and give it a game like, say, chess and ask it to beat Kasparov? The answer turns out no, because it's been trained very, very narrowly on the moves of Go game. So what happens is the moment you take a very high performance AI program, which is very good at performing a narrow task, to a different domain, it fails. That's why it's called narrow AI or weak AI. So what is the expectation? The expectation is without much retraining, understanding the context in which the application is being executed, the environment in which it's being executed, the game is being worked on, the nature of task is being worked on, the program can understand, reason, and reconfigure itself to play or to perform in the new environment without much retraining. That is more important. And that is what is the expectation from general AI or strong AI, or what we call as, human level general intelligence. Today, unfortunately, a very simple facet of humans, which is the dynamic reconfigurability of human intelligence, like if you suppose learn right-hand driving in some city where it is right-hand driving, like India, you go to US, which is left-hand driving. I don't think it takes too much time for a human driver to pick up. It takes a little orientation for 1 or 2 days, and then he is up running on the American highways. That's the kind of dynamic reconfigurability which humans perform, humans are capable of, which is not possible to be displayed in these systems, which are very good at single task champions. AlphaGo cannot play chess. Similarly, a American car driver on American roads cannot go and perform the same level of autonomy on the UK roads or Mexican roads. So when I say AGI, that is what we call about expectation of human level general intelligence, which is also called a strong AI. And unfortunately, today there are several facets of AI which are inherent to AGI, which are not still displayed by ANI. Let us take a very simple facet of AGI, which is still under research as to how to bring that into ANI systems. The ability to reason with what we call as uncertainty. Today, most of the applications in AI world are dealing with scenarios where it is possible that there are multiple kinds of truth for the same argument. For example, for some people, some argument may appear true, some argument may appear false for some others. So this kind of existence of multifaceted truth is something which the digital world does not understand, because digital world is based on the idea of 0 and 1. So such multifaceted truth is inherent in a behavior which is essential for AGI, which is called as the notion of non-monotonic reasoning, or the notion of uncertain reasoning, which is basically not possible in conventional digital kind of mode where we are used to the 0-1 kind of logics. Whereas we have other logics which are being built to handle AGI scenarios, like modal logic, which is talking about, don't just talk about 0 or 1, but we talk about phenomena like there is a possibility of something, or there is a necessity of something. Or we have other kinds of logics like, very, very close to human kind of thinking, known as autoepistemic logic, which talks about belief. It's about, I believe certain fact to happen. It does not talk about a fact as 0 or 1, but there is a gray area of the fuzziness of potential truth. And that fuzziness is exactly what is absent in current narrow intelligence systems. And that is one area where there's a lot of important gaps which need to be filled up in building a resilient general purpose, general AI level system, which can be considered as narrow plus 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 plus. And that to me is probably a couple of decades away. There are several other facets of AGI which are not in ANI. I can go on and on. Like, for example, there is also a reason nowadays that people talk about, can I modify my state depending on the context? Contextually, can I adapt myself depending upon analysis of the environment in which I am automatically without having an external input for training or etc. So that contextual adaptation is something which is not there in current ANI systems. So given these kind of facets, which are gaps between AGI and ANI, which may take a couple of decades to solve, we see that AGI is a couple of years away, a couple of decades away maybe. Then comes the notion of, okay, once we have achieved human level AGI, machines are talking about human level performance in all tasks, dynamic reconfigurability at the level of humans. What does it mean if humans are superseded by these machines? That is the fear mongering which a lot of practitioners and thought leaders have expressed fear of. It might be true that AI of such machines will be creating, some kind of a super machine which are smarter than the best brains in every field, with creativity, general wisdom, empathy, social skills, and at the same time, outpowering in computational efficiency than humans. That is a scenario where we call a super intelligence, artificial super intelligence, and that's what sometimes the bigger thought leaders like Elon Musk have talked about, the potential for super intelligent machines taking over, the basic daily lives of humans, and sometimes it may be overpowering humans. What happens in that world where if they come and superpower over humans? And that is a scary scenario. But let me tell you what happens in all of these systems which are being endowed with software which is giving them the inherent intelligence. There is always a what I call in colloquial terms as a control C button. Control C button is like, whenever something goes in infinite loop in a personal computer, we bring the computer back to our context, and that is what we call as the interrupt. And so what we believe is, even though we believe that systems can be made super intelligent, but the control will still remain in the designers who are still humans and who will retain interrupts and fail-safe mechanisms to bring control back to humans. So that is similar to, if you remember the movie Enkiran or Robot, right? In that, there is a red button. If you remember the, robot which had gone rogue, but with that red button being removed, it could come back to control. That is the red button I'm talking about. So while we talk about AI affecting our human lives, it's not like all lives are being affected in the same manner, but we're talking about only specific level of AI as prevalent today, which is the level of artificial narrow intelligence or weak AI, which is talking about an AI which is very good at one single task and which is very good at performing that better than the best of the best human brains. Now, when I say human level behavior, what is the constituent technologies? What are the constituent elements? So if you see, the main brain of human intelligence is what I call as reasoning. Reasoning is what I call as the brain of AI, in the sense that if any human intelligent system has to be emulated, you have to inculcate reasoning into that system. The reasoning again can be of two types. The one where we talk about, give tons of raw data, try to make the system, which is going to be enabled, learn patterns from that, and extract rules from the raw data so that the rules define the patterns. So what you're doing is you're shrinking the knowledge from huge amounts of raw data to a very concise form of knowledge, which is the rules extracted from that. And the rules represent the patterns which are present in the data which is fed to it. So going forward, you don't need the whole data, but you can work with the patterns you've extracted. So that is the magic world of machine learning, which we're going to talk about in a little while. And a lot of the talks in this conference are going to be primarily about this particular brain of AI called machine learning, which is fundamentally, from a logical reasoning perspective, it is also known as inductive reasoning. Meaning, inductive means it says from a lot of special facts, you try to generalize and bring general rules, general patterns. That's called inductive reasoning. And today, machine learning is a form of inductive reasoning, which is able to give concise patterns extraction from large amounts of raw data, which is what is giving us the huge benefits of applications like cancer diagnosis or driverless cars or game playing or detecting malignant tumors, etc., etc. On the other hand, the other way of creating new knowledge is the other way, where you have a lot of domain knowledge which you have written in form of rules, which you have written in form of patterns, and from those patterns and some facts you try to derive new facts as they come. Why I'm talking about this is important is because without this kind of a mechanism of deriving new facts from existing rules or patterns and existing facts, what you would do is you would end up working with what I call as a conventional notion of a database. Because what is a database? A database would be nothing but a collection of infinite number of raw facts. Each row is a fact. But if you were to collect all the facts in the universe and keep them as a database, that would be very inefficient. And that's what we see in intelligent systems. In fact, earlier versions of AI systems in 70s, 80s focused a lot on this model of reasoning called as deductive reasoning. In fact, this is very old. This is one of the oldest form of AI invented by people like Aristotle and Plato. Later, in fact, perfected by concepts like Euclid. Most of you have read Euclidean geometry in your mathematics in grades 8, 9, 10, etc. Or if you've done principles of mathematical induction, that's classic example of logical reasoning based on deductive principles. So what they do is they keep a set of logical rules. And in classical geometry, if you remember, you had a set of axioms. Using these axioms, you had to derive new theorems. So theorems were not meant as raw facts which were given to you, but they were to be derived from application of axioms. Same thing, axioms here are logical rules, and based on existing facts and logical rules, you derive new facts. And that is the benefit of having a logical reasoning mechanism as part of AI systems, is that you don't have to capture all the raw data. Instead, you can derive them by combining rules and facts. I'll give one simple example. Let us say I was supposed to create a quiz program like Watson, IBM Watson, which is the world famous Jeopardy winning champion software program, which beat world Jeopardy champion. What is Jeopardy? It's a world quiz program. Now, suppose I give it a question saying that, can you tell me the capital of the country with the second largest population in the world? Naturally, you would expect that if it was a database, such fact would be available as is in the knowledge base or in the database. But unfortunately, you don't have. You have two separate knowledge facts. Capital of India is Delhi. India is the second most populous country of the world. So what happens in such kind of scenario? What happens is you try to look at combining the logic of both facts and derive the new fact, and that too dynamically, because you have to be faster in deriving the fact better than the human champion. So without deductive reasoning, you would not be able to develop a reasonably comprehensive AI system. So there are several tons of examples where you need a combination. Sometimes you need machine learning, sometimes you need deductive reasoning in order for us to get a true AI. So the earlier versions of AI, which was very successful in 80s, was primarily based on deductive reasoning, also known as the era of expert systems, where humans wrote a lot of logical rules, and based on the domain rules and the facts, you could always derive facts from these, and those became very popular in those days. But today we have a different approach, which is basically data-driven, where you collect a lot of data, give it to a machine learning model to extract patterns, and we will get an inductive machine learning system. But as we go forward, already in the research community, we are seeing that the machine learning models based on purely inductive reasoning and deep learning are bound to fail. They are successful today in a run-of-the-mill like deep learning with driverless cars, cancer. These are all okay, but they're all magic, nothing but voodoo magic. So the voodoo magic, is it not successful? Yes, it is successful. People are accepting it, but there's a limit to what you can do, because today, for example, I will ask a simple question. I expect people to answer in the chat. So the answer I want all of you to talk about is, suppose I have given a robot a scissor and knife, and you are put on the operating table, and I will tell you as a confident that this is the world's best deep learning trained a robot showing 99.9% accuracy. But I don't know what the internal, how it's been replaced, how it's been capturing its knowledge. But this model is wonderful. It worked 99.9% in the past. Will you allow that person or robot to cut your body and run the operation? I would like some answers in the text. I'll wait 2 minutes. Okay. So in just a sample of a few, except one, all of them have said no. So this is exactly what I'm trying to tell you when I say that we are in the era of what we call as black box AI. And the phenomena which we are relying on is the phenomena of machine learning enabled black box systems, which we cannot explain how it's working, but it's working to the best. There's a best driver taking care of a car, there's a best surgeon taking care of a body. That's not enough. That is the reason why we need deductive systems. So today there's a lot of awakening in the AI community about merging symbolic systems based on deductive systems and inductive systems, so that you can derive some rational explanation of why some system is successful, extracting some potential causal analysis of what rules are guiding the underlying principles. So there's a intersection called explainable AI, which is deriving patterns which are legible for humans to be understanding the causality of why the system is behaving. And that is why we see that going forward, we will see a system where the current modern world of voodoo magic of deep learning will work along with conventional, logical, scientific, symbolic AI and come up with the best of both worlds. That does not mean that today there are a lot of funded startups which are working in deep learning based startups. Then there's no harm. We will let that go on. But as we see more and more human capabilities being given to machines, there will be a balance. We will see derivation of newer streams of work in deep learning where people will ask for explanations called explainable AI. Explain the rationale behind your work. So that is what I meant by saying that the future is a coexistent world of symbolic and connectionist AI, which is the inductive machine learning. Given this, the next fact, which is also important for us to understand why AI is popular. We work on raw data to create inductive patterns, machine learning on data. But what data? The data we talk about is of all kinds. We can talk about structured tabular data, Excel kind of data, database table data. Or we talk about speech data. We talk about language and text data. We talk about image data. We talk about video data. Because of being able to work on all these kinds of data and being able to apply both inductive and deductive, whether you extract patterns or you exploit logic, we're talking about both being applied on all this data. We see diversity of applications. Example, let us look at the chatbots which we speak to, for example, Alexa or Siri or Google Now. That's speech understanding. On the other hand, when you give a Google search, it tries to predict what you're going to search. That's a language text input. On the other hand, when you look at a cancer phenomena of a radiologist output, and it is giving you automatically whether it's containing a cancer or not, the X-ray, it is image understanding. On the other hand, a driverless car looks around, captures a video around, and understands what is happening around and analyzes the video to find out what direction it should go. That is video analysis. So if you look at what we work on in terms of applying these reasoning phenomena is on these kinds of varieties of data, which is what exactly humans do. We see, we talk, we listen. But unfortunately, two facets of human senses are still not captured by AI. can I know in the chat, what are those two facets, two human senses are still not captured by AI programs? What are those two senses? Smell sense, perfect. Then taste is not purely touch. So if you look at, primarily we talk about smell and touch, and that is something which is still not in the domain of what we call as AI programs. So maybe in the future we'll see olfactory computers or tactile computers which are intelligent. But today when we talk about, it's primarily about perception of language, perception of speech, or perception of sight. These are the three primary capabilities of AI systems. But then when you develop these systems, one thing you got to understand is, when you talk about AI as a pattern extraction from data, it is not that there's only one pattern which can explain the best possible way to derive pattern from the data. There may be several patterns which may equally explain the data. So there, what we need to do is we need to search among many possible solutions. But when possible solutions are many, we need to ultimately give one possible model, right? One possible pattern which is required to be given to the end user so that he can take that as the representative of the raw data. There we see optimization coming into the picture. That while it is a search for a pattern among many possible patterns, what we want to do is take one of them as potential output. Let's say we talk about a line, linear line explaining the relations between output and input variables. But if we have many possible lines explaining, we're not interested. We want one line to be output. The one line, we call it as optimization. That one line we need to develop based on an optimality criteria, because it cannot be possible that I will work with infinite number of patterns from the raw data. Because ultimately we have to work on a summarized pattern from the raw data. That's what is the goal of machine learning. And with that, we talk about converting a notion of optimization, which may be, in case of linear regression, it is minimizing loss function, which is the difference between expected and obtained data, which is sigma yi minus fxi plus p whole square. That is basically mean square error. In another case, for example, in a neural network, it could be about back propagating based on the log loss, again, difference between expected and what you got. Or in case of a classification problem, it could be about maximizing accuracy, which is about making sure that out of the whole set of expected outputs, which one is giving you the best possible set of correct explanations. So the optimization routine is important to help us select one among the many possible solutions. But then one also important thing you got to understand is that it's not like you are allowed all the possible solutions, even though they may be solutions to the problem. Let us say we have to go from one point of a city to another point of the road, another point of the city in the road, on road. Or maybe let's say we just have to go from one point in the map to another point of the map. Can we just use the notion of optimization, saying that we'll take the shortest path going from one point to the other? Shortest path is a straight line joining both points, right? And this one, if you see on the map, it is possible that it is cutting through, buildings, parks, maybe street lights, maybe cutting through rivers. Is that a path you want to take in going from one place to another? The answer is no. If you have to take a cab, you can only go through designated roads. So what is that? That's a constraint on what potential solutions you can take. It's not like you can take any path, any possible solution. So there are constraints in what solutions can apply. Let's take the same thing. Suppose you're defining a chess program. It's not like you can get the chess program to run any possible move depend on an optimality criteria as to which is the shortest move, because each move again is subject to constraints. Like for example, queen can take only these moves, or a horse can take only these moves. So each piece takes only certain constrained moves. So if you see, the process of coming to an AI solution is basically a search, because there are many possible solutions. Again, when we search for one optimal solution based on optimality criteria. Then when we talk about all the constraints which are governing the solution, we have to make that guiding process of which should be allowed, which should not be allowed in terms of potential solution. So if you see overall AI, I'll dictate in a word form. AI is the overall process of reasoning from raw data to create patterns or new facts, where raw data can be structured speech, language, text, image, or video, subject to the search for the optimal pattern with keeping in view the constraints in mind. So to me, that is the technical meaning of AI, instead of just talking about, let us say, simple human level intelligence exhibited by an intelligent agent. So don't you think now you have a solid understanding of what are the three components of AI? Reasoning, data analysis, and the notion of how you work with constraints, search, and optimization. That's what this whole conundrum is all about. Now, having said that, what is the brain? We said the brain is machine learning. What is machine learning? As I said, it's basically pattern extraction from raw data. Raw data, we call it as experience. And the pattern we extract from that, we call it as learned pattern. So machine learning is said to be learning from past data or experience. If it extracts the pattern, but another two characteristics are very important. One is that experience which it is providing as input, it is not requiring any human intervention into the structure of what pattern to extract. Instead, it is extracting the pattern without being programmed directly from the raw data. Second thing is, as we get more and more data and feed algorithms to it, it can extract better pattern. So the performance of the pattern improves with better and better data, or more and more data. So what are the key important things? Machine learning is about pattern extraction from data. That's why it's called machine learning from raw data. We also call it experience. The experience is fed to the algorithm to extract the pattern, and the pattern is extracted without being explicitly programmed by a human being. Whereas if you get more and more data being fed to the program, you can get better and better pattern. So the task performance of the specific pattern becomes better. And in doing such a definition, one important thing which comes out to the mind is that ML is basically a probabilistic science. It's not engineering. When I say engineering, I know if I know the exact specification which I give it to, say, a carpenter to build, say, a desk. I know the dimensions, I give the design, and when I see the finished product, I can verify if there's a deviation from the design I manufactured. Is there a protrusion at some point which is not according to specification? But in AI, from the raw data, I cannot specify that this is the expected exact pattern which I'm talking about. The reason is we're talking about a fuzzy notion of a pattern which is explaining the hidden truth, or what we call as the intuitive relationship among the data. So when I take such a resort to a pattern which is uncertain, we always embrace fuzziness. So we understand that there is a mathematical explanation to the pattern inside the data, which is most likely based on a notion of optimality. So we will say with a high degree of probability, the pattern to be applicable as for your particular data. That's why when you create a ML pattern out of raw data, you always say that this is with this degree of confidence that we feel that this model is going to explain the pattern in the raw data. So what could be grade? It could be about a percentage of accuracy is a measure, or it could be in a probabilistic terms like almost certain, highly likely, very good chance, probable, better than even, chances are slight, rare. So we can use a graded probability like this. So depending upon shades of gray, or a more solid example of a pattern, or a notion of realistic error, we say that within the permissible error, we say that this is my final model or pattern extracted from data. So what happens, just like Cavendish, Newton, all of them did scientists' experiments based on science, where they say that they had a rough hunch that this is the kind of expected result. They never went to saying that this is the exact result that's going to come. So in science, we always deal with forming a hypothesis. We try to come up with a good possibility of being able to prove the hypothesis. Same thing happens in machine learning. We prove a hypothesis with a high degree of probability rather than saying that with a certain greatest possibility is what we talk about. We never say this is 100% certain, this is a rule exactly which works. In fact, if we work with 100% certainty, then it is bad for us because it's possible that it's very tightly fitting your current data. It may not be very good for generalizing to newer data when it comes. So it's important to keep that element of fuzziness or probability into your machine learning. Then the second aspect which comes out from this is very important. In any conventional program, say a C program you've written, you always test it based on, okay, you written a program, I know that if I give this input, I expect a certain output. So that's called as a test oracle. So you can test these programs by notion of what we call as a test oracle, because you know the expected output for a given test input. That's not possible here because there is no concept of a perfect input-output combination because of the probabilistic nature. So we cannot work with a perfect notion of testing AI programs. So we work with the notion of what is known as pseudo-oracles. But that's a bit complex subject, but let's not worry about it. So what happens in ML is, interestingly, conventionally in program, we give data in, data out, and you verify the relation between expected data and what you got. But in ML, you give in data, you expect a program out. So ML is interestingly not the same as conventional program, it's the opposite, where you give data in, you expect a program out. So there is no way you can control the program. In conventional program, you can control the logic, exception logic, or if then else loop, or different conditions you can put. But here, your hands are tied. So in machine learning, the only way you can change your program or the model is by changing the data. So that's one key important thing you need to take away. So when you talk about machine learning, again, not one size fits all. There are three kinds of machine learning depending upon the level of data available to you. The most important, what we call as, is the supervised machine learning, where we talk about there is a set of input data and there is some expected output data also. So this is, for example, let's take a cancer detection scenario for X-rays. We have X-rays as input. We know the expected output, which is whether it's going to be cancerous or not. Or let's take, we know the past history of how a stock has performed. And based on that, you want to predict tomorrow's stock price. So there, you know the expected output. So there is a set of X variables and there is Y variable. That is why we call it as supervised learning, where you try to find the relationship between input and output variable as the machine learning problem. But then what happens is the output variable can be very few values. Like, for example, in cancer case, it's either cancerous or not. Such kind of examples are called classification machine learning, supervised classification. Other case where I'm trying to predict a value, like, for example, I'm predicting a stock market value, it's called regression. And that kind of systems are very useful when you talk about stock market prediction, weather prediction, fuel efficiency prediction, or you're predicting risk potential of a customer, etc., in some kind of a score. All that becomes regression. Whereas if you have discrete variables output, like for example, you're recognizing digits, there are only 10 values. You have handwritten digit, you're recognizing it as 1 of the 10. So this kind of finite number of outputs calls it classification. So supervised is the most common types of machine learning studied today. 90% of problems today are supervised learning. But what happens if you don't have any output variable? You only have raw data. You would extract patterns from that. That kind of machine learning is called unsupervised machine learning. So there, what you do is you try to extract simple patterns from the raw data, and that's called as unsupervised machine learning. Several flavors of patterns exist. Simplest pattern I think of is what is called as clustering. What you do in clustering is you just try to find out the different groups of homogeneous kind of like behavior data and form groups of such similar data. And that is called clusters. Very useful in market research, where you find out similar customers and group them together. Second type of work is where we use recommendation systems in systems like Amazon or Flipkart, where you see when you're buying, you see that when you put something in a shopping cart, you get a prompt. People who have bought this also bought this. So do you want to add this to your shopping cart? What is the Flipkart or Amazon doing? It's looking at past history of what people have bought together in a market basket, analyzes that, and if you buy one of them, it's trying to figure out if it can upsell other items to you. That is known as association rule mining. Like that, you can do different other kinds of extraction of raw patterns from raw data. That is what we call as unsupervised learning. But in both unsupervised and supervised, you have historical data available, which is also known as experience. But when we talk about a third category of experience, kind of which is based on the notion that I will create an AI system which starts with zero experience. But when it is made to run on a practical problem, it learns from experience as it runs through several rounds of that problem. Like, for example, if you're going from one corner to another and you're a blind person, what happens is, based on facing an obstacle at a specific point, you may fall. But as you do more and more times you go through the process, you will know that at specific points there are these obstacles. You will avoid them. You will take a different path. So over time, it becomes smart. And that is very important for understanding of reinforcement learning. So reinforcement learning is starting from zero experience, but you build experience as you go along. So how does it work? It's based on idea of you give rewards or punishments at every move. Based on that, it accumulates this data, and based on some notions of algorithms like Q-learning, it creates an accumulated score, and it becomes much smarter as it goes along. So we have broadly these three kinds of machine learning. Depending upon the use case, you might have to fit one or more types of this machine learning. But these are the three broad categories of machine learning, which is very important. But what happens when you talk about dealing with unstructured data, like say you're talking about take a cancer image, you want to extract that in form of whether there is cancer or not. What happens is, conventionally, since you're talking about supervised classification, you need input data. So input, you used to extract raw variables from the image, saying that, okay, what is the length of the lesion? What was the intensity of the lesion? What was the thickness or diameter of the overall lesion you found? Or what is the overall percentage of the lesion with respect to the overall image of the part? Like that, you would create some artificial variables and create XY variables, and then feed it to a machine learning algorithm. But here, that's where deep learning comes to the rescue. In the recent past, about not more than 10 years back, we saw the emergence of a subcategory of machine learning where they said that instead of writing all the facts of the input as X variables, which are well-known structured columns, can I give the raw data itself and let it figure out the features automatically from the raw data? That is what is called as deep learning, where you learn a hierarchy of concepts from a raw data. So what it does is, given a raw data, it extracts hierarchy of patterns automatically from the raw data, which you can further feed into a classification or a regression, whichever. But think about this. Suppose I have an image called 4 p.m. At the bottommost, it extracts edges. From the collection of edges, it forms strokes. Then from there, it forms characters. From their characters, it may form, saying, some temporal meaning. Then from actual meaning, like a meeting time confirmation. So you extract this automatically from the raw data rather than saying that I will mean this to this X and Y, X1, X2, X3 features, which I derive manually from that. Once you derive this automatically, then this can be used for appropriate machine learning task. It could be a classification task. For example, you take the features extracted from a cancer image and feed it to a classification, saying that is it cancerous or not. Same thing, you take a speech data, you can extract features from there. Same thing, you can do a NLP text, extract features from there. So what deep learning does is it helps us in creating a layered automated features extraction from raw unstructured data and feeds it to conventional machine learning algorithms. This revolutionized the whole purpose of AI and made sure that tons of applications became useful for AI, which are based on dealing with text, image, video, or speech. That's why today deep learning is considered the heart of AI. But deep learning, you should not forget, it's still a kind of machine learning where there is supervised machine or unsupervised or reinforcement. It can work on structured data or unstructured data with deep learning or without deep learning with conventional machine learning algorithms. Now, AI overall you saw is beyond machine learning with inductive and deductive reasoning. And deductive reasoning is beyond machine learning as part of AI, but not part of machine learning. So this is the overall relationship. Now we see that if you want to do all of this, is it that we can do all of this in no time? You need to understand that just like we have software development life cycle, where you do requirements, then architecture, design, code, then do test, and then deploy, in machine learning also we have to follow the life cycle. Acquire data required for a problem, develop a business understanding and see what data is required for that business model, business with powered by AI. prepare the data, clean the data, then form the hypothesis as to what kind of machine learning problem is it, supervised classification or supervised regression or unsupervised clustering. Then you run multiple algorithms to get the process of the model extraction from the data. Then what you do is you evaluate whether it is the best model you can choose among many possible models. Once you have captured the perfect model, you go and deploy in the field. For example, you've deployed a machine learning model to detect cancer in X-rays. You have done a lot of analysis of algorithms of extracting data from cancerous images. Take that model and now put it into the field where you get a radiologist workbench where he uploads a new X-ray. Then your program will tell it whether it is actually cancerous or not. So that's what we call as deployment. And then when you deploy it over a period of time, it's possible that the underlying pattern in the data is changing because of change in the underlying truth in the data. It could be because of what we call as the concept drift phenomena. Concept drift phenomena is nothing but the underlying truth in the data keeps changing over time. For example, if you are recognizing fashion trends by machine learning, every quarter, I'm sure the customers change their fashion trend. So if you have created a fashion mechanism for machine learning over the past, previous generation, which is previous quarter trend, it may not be applicable for this quarter's trend. So you have to go back to the drawing table, start the whole process of data acquisition again. So that's why this is a cyclic process. And one key fact of the matter is, this is something important for you students, is 80% of the time is spent in data acquisition and data preparation. There is very little time spent in machine learning part, which is hypothesis and model evaluation. So don't get enamored by machine learning models, which are all these different methods for regression, classification, and different kinds of techniques. These play very little role. More important thing is, how do you talk about the business problem, understand what the data required for it, write scripts for getting data, beg, borrow, or steal, but get the data. If you don't have data, there's no AI. Clean the data. If you don't have clean data, you'll get junk in, junk out. 80% of the time is about writing scripts to clean, remove outliers, remove features, making your own features, extracting of features, removing features, trying out different features, etc. That's data preparation. So lastly, these are the basic broad applications where we're seeing sky's the limit for AI today. We have all the may I help you bots. We have driverless car, truck, golf cart, bus. Name a vehicle, we're getting driverless. Game champions, name a game. We have today Go champion, we have chess champion, we have poker champion. Your friendly AI doctor or radiologist, replacing doctors or radiologists with AI-based scanners. Self-healing machines, industrial machinery, understanding what the problem is, diagnosing it, and repairing themselves. Cashierless retail store. If you say Amazon example of the latest stores where there's no single cashier, you just pick items, put in your shopping cart, and walk out. It's called just walk out technology. Radically personal digital education in the current world of stay-at-home online education. People are trying with platforms where you get personalized content based on your speed, your understanding, your likes, learning path, which is very personalized and n equal to 1 to you. They don't want to feed everybody the same material. So with this, I'd like to stop here, and I would like you to see, this is our YouTube channel.